down so it's not overbearing. Hello everybody, hello. We're gonna get this show on the road. You know it's gonna be a good show when everybody's a couple minutes late. How's everybody doing tonight? That was okay. We all made it back to dry land after the heavy rain. Come on, we're doing okay. How's everyone doing? Nice, nice. All right. My name is Aaron. Erica up here. Tracy's in the house. Adam and Brian are running the show, making sure everything's good. Sam, and I don't know where Sam is. Sam is doing Sam things. Michael, I think, is home. Thomas is online. Jasmine's at home. Caleb's here doing double time. I always forget my intros, and that's okay. I said what our names are. How many, I recognize a lot of faces. How many people are coming out, at least for the second time tonight? Show of hands. Good to see everyone. How many first timers out here tonight?
Yeah.
Nice. All right, cool. Good to have you. Gonna learn a thing or two, gonna drink a lot. For the first timers, Erica, would you like to tell them what Astronomy on Tap is?
Absolutely. So, what is Astronomy on Tap? Well, most importantly, it is an international event. We have locations all over the US, Europe, and a smattering of other places around the world. Each location is independently run, usually by various scientists and, in our case, grad students in the area. So we're all volunteers doing our best. So, in particular for San Antonio AOT, what are we? We're interesting. We always have some great talks lined up. We have our lovely Tom here today, and then Caleb will be filling in. We unfortunately had one of our speakers get ill at the last second, so we had to scramble a bit. It's always fun. We try to do trivia at the end of the night, so you can win some fun astronomy-themed prizes with some usually astronomy-themed trivia, but not always. When in doubt, blame Sam if the trivia is annoying. And most importantly, it is interactive. So there's a phone number on the screen behind me over here. So you will be able to send in questions that we will then ask the speakers at the end of their talks. So make sure if you have questions, text that number.
Don't be weird.
Don't be weird. We will be filtering the questions. So we want to first start off with a little public service announcement from Tracy. So.
Okay, hey everyone, it's great to see everybody here. A couple of cool things to say before I bring it down just a little bit. First, one of our speakers here today is here with the Juno mission. We have a Juno mission team meeting going on at Sperry, so welcome Tom and any other Juno folks. I'm also going to highlight that we just started this week. Our interns from the Europa Clipper Icons program are here tonight. So these are college students from all over the country coming to work with us for the summer. Welcome. Okay, and on slightly less fun news, let's start this one. So as you guys know, there was a presidential budget that was released. This is the amount of missions that are currently existing in space that are part of the NASA science fleet. As a private citizen, what I'm going to suggest is if you don't want to see all of these missions that are currently perfectly operating missions that have red slashes across them disappear, to let your senators know that you support NASA science and you don't want to see such missions disappear. We would lose missions including Juno, including New Horizons that flew by Pluto, and many missions that are studying and monitoring the Earth. So there's a lot at stake, and so we need the public, if they are interested in maintaining these science programs, to go ahead and let your representatives know. And there's a really cool tool that you guys can use. What I recommend is going to the Planetary Society's website. They have a lot of information, a lot of action items that you guys can do. But really cool is, this is just a screenshot, but there's a website that you can actually go by district to see how much money NASA invests in your district by paying, through grants or contracts or STEM education, and how much money that generates. So every dollar that NASA puts into an area generates usually on order of 3 to 10 times as much money as it was actually input into that location. So it's a really powerful tool if you want to use that to call your senator or your representative. Check that out at theplanetaryScience.org. And other than that, that's all I have to say. So thanks for listening to this public service announcement. And we have a really great show tonight, so we'll bring it back.
All right, on for tonight's schedule, we have Dr. Tom Nordheim talking about Europa, Jupiter's radiation-blasted ocean world from the moon, or ocean world moon, not from the moon, little m. We have Astronomy in the news, and then Mr. Caleb Gimar is going to talk about how to give an excellent presentation at the last possible minute. Going to give us a master class, and then we're going to have the world's greatest trivia, brought to you by Sam at samuel.hart@sawyer.org if you have any problems. First up, we're going to have Dr. Todd Nordheim. Pull out my handy phone. Tom is a member of the senior professional staff at the Johns Hopkins Applied Physics Laboratory, APL, in Laurel, Maryland. Prior to joining APL, he spent 8 years at the NASA Jet Propulsion Laboratory in California, first as a postdoc and later as a research scientist. His research focuses on potentially habitable icy moons in the outer solar system and how these objects interact with their space plasma and radiation environments. Dr. Tom Nordheim, everybody. And then, gonna back up. So for the uninitiated, we have what's called a drinking word. It's very straightforward. You hear the word, you drink. What is your drinking word?
Tonight's drinking word is life.
All right. Drink responsibly. Down is next.
All right. So today we'll be talking about Jupiter's radiation-blasted moon, Europa. And first of all, as mentioned, Europa is a moon of Jupiter. It's one of the 4 major moons of Jupiter. And here you can see this beautiful image that was captured by the Juno mission that Tracy just mentioned. And Juno is this beautiful spacecraft that's been in orbit around Jupiter since 2016. It also has a really fun local connection because Juno is actually led out of the Southwest Research Institute here in San Antonio. Now, among other things, Juno has studied Europa. And this is a picture of Europa. And for those of you who may not be used to looking at pictures of outer planet moons, this is a very striking and startling kind of surface that we're looking at. It's crisscrossed by these fractures. It doesn't have a lot of craters, which means that it's very young in geologic kind of context. It's a very young surface that seems to be refreshed on a gradual, ongoing basis, probably. And as you can see, it's covered by these long cracks that crisscross the surface. And these cracks seem to be correlated with this kind of reddish-brown material. And when we really zoom in on the highest resolution images of Europa's surface, we see a surface that's really marred and pockmarked with these really weird, chaotic surface textures. And when we zoom in on these fractures, we see that really that red material is very, very closely associated with those fractures. And that's interesting because we think that we know Europa has a subsurface ocean. There's an icy crust made of water ice, no real atmosphere to speak of, and there's a massive saltwater ocean beneath the surface that has more liquid water in it than all of the Earth's oceans combined. And it's also very exciting in the search for life beyond Earth. And so we think this ocean, we think there might be hydrothermal vents at the bottom of the ocean, interactions between the silicate mantle of the moon and the ocean water. And on Earth, we think one of the leading hypotheses for how life formed on the Earth is around these hydrothermal vents at the bottom of the ocean. So we have this vast ocean, it might be habitable, and we also have some indications that these disrupted terrains on the surface might be connected down to the ocean beneath, maybe through cracks or maybe even through plumes erupting from the surface. Then this is really exciting because we know then that there may be material from the ocean being transported to the surface, possibly even signs of life. And this is just showing you a little bit of our strategy for exploring Europa. So we have Juno in orbit around Jupiter right now, studying the planet and its moons and rings. But we have an upcoming mission that has a strong involvement, again from San Antonio and again from Southwest Research, called Europa Clipper. That's going to be arriving in 2030. It's going to be flying by Europa a bunch of times and trying to kind of remotely study the properties of its ocean and ice shell, and trying to look at some of that material that might be coming up from the ocean, and trying to, by looking at that, trying to understand what the conditions of the ocean might be and if they're indeed conducive to life. Now, we'd like to go much further than that in the future. We spent a lot of time working on a possible mission that didn't end up going forward, but may go forward in the future, called Europa Lander. And so that actually would take the next step and go and land in some of this reddish material, maybe, and try and sample directly and look for signs of life. And in the future, you know, we can get really creative and think about exciting concepts, maybe submarines or under ice rovers that could go all the way into that ocean and search for signs of life. Now, there is a little wrinkle in the story, though, and that is that Europa orbits within Jupiter's magnetosphere, its magnetic field. And Jupiter's magnetosphere is the harshest radiation environment in the entire solar system outside of the sun. And this is a plot of basically the radiation intensity that the Juno spacecraft has measured. And you see Europa here is pretty close to that super high radiation region. And in fact, the radiation environment, if you stood on the surface of Europa, so to get a lethal dose, a human being has to get about 1,000 rads. That's a measure of radiation dose. And on the surface of Europa, you would get that in less than a minute. And so it's really like standing, looking into a particle accelerator or being inside a nuclear power plant. You would be dead pretty quickly. And what's really interesting with Europa is that it seems like radiation actually might be really shaping the surface and shaping what we see there. So this is an image from an earlier mission called Galileo, and it found this kind of blot of mysterious kind of unknown material on the surface of Europa that's concentrated in a very specific location on the moon's trailing hemisphere. And there were a lot of different explanations kind of that people came up with for this. One could be that it's sulfuric acid being produced by the radiation interaction with the surface ice. There's an idea that it could be salts coming up from the ocean below. And there's kind of a mix of both, where it might actually be salts that are coming up and then being transformed by radiation into a different kind of salt, actually. And so what I want to say here is really that that surface of Europa is like just totally shaped by this constant blast of radiation. And it's a really unique environment in the solar system where maybe the major geologic process happening, modification process, is actually radiation induced. So how does that relate to life? Well, so let's say we wanted to go land on the surface of Europa and look for signs of life. And here we have a very enthusiastic, optimistic schematic where we have these vents on the ocean floor, and we have these cracks, and we have vents just spewing out material. And so if we had, let's say, signs of life, biomolecules, in this material being deposited on the surface, as soon as they end up get onto Europa's surface, they start getting degraded very rapidly by radiation. And so really, if we want to go look for material on the surface of Europa, or study it remotely with cameras and spectrometers like the upcoming Europa Clipper mission is going to do, we need to understand how much has this material been modified by the radiation, because that tells us if what we're seeing is really indicative of what the conditions in the ocean are, or if it's been totally modified. Now, this is kind of a map of the radiation flux on the surface of Europa. And it's showing that the radiation is really, we think it really ends up in very specific regions. And this predicted pattern of where the radiation ends up is very similar to that mystery material that I showed you in a few slides back. So that's telling us that this material is probably very strongly controlled by the radiation bombarding the surface. So it's really like modifying the surface composition and chemistry. But bringing it back to life again, there is another aspect of radiation that's very important to the possible life on Europa. And drink. So we know that life, it requires certain things. It requires liquid water. It requires the chemical components, basic chemical components that life needs to exist. We call them schnapps, which is very appropriate. But we also need a source of energy. And life on Earth very strongly uses photosynthesis and sunlight, basically, for its energy source. But below maybe 10, 30 kilometers, a number of miles for you Americans, underneath the ice, there is no sunlight. So if there is life in Europa's ocean, it's going to need a different source of energy. And another possible source of energy is using chemical reactions to power your metabolism. And there are some examples of life on Earth that does that, for example, in the deep oceans. So this brings us back to Juno and a very exciting discovery, actually, that was made when Juno flew by Europa in 2022. And so we actually detected evidence of oxygen being produced on the surface ice of Europa by radiation breaking down the water molecules and producing things like O2, oxygen, and hydrogen peroxide, like you might have in your medicine cabinet at home. And those are very powerful oxidants that, if these get transported into Europa's ocean, life in the ocean could use that to power their metabolism, use it as food, basically. And so it's kind of exciting that Juno has actually detected the possible food that life on Europa could be eating. And here's a little schematic of the Juno spacecraft flying by Europa here and detecting these oxygen, evidence of these oxygen ions. So, looking forward, we have this very exciting Europa Clipper mission happening. It launched last year. Tracy, Ujwal back there, and a number of others were there for this launch at Cape Canaveral in Florida. We weathered a very large hurricane, tornadoes that hit our hotel. We were sheltering with our families in the conference room. It was very exciting. But it was a beautiful launch. So we launched on a Falcon Heavy rocket. Launch went flawlessly. Spacecraft has been operating flawlessly. So that's going to be arriving at Europa and Jupiter in 2030. But that's a long time from now. And right now, we have this beautiful spacecraft called Juno that's in orbit around Jupiter, taking new observations of the moons and doing fantastic science. And as Tracy mentioned earlier, in the President's NASA budget that came out on Friday, this perfectly healthy, very, very productive science mission would be canceled. And so I just want to give it some perspective that the cost of this mission, to keep this mission going, could you guys guess how much each taxpayer would have to pay to keep this mission alive? Okay, so we have a few cents, we have fractions of a cent. Anyone else? $10. Okay, thank you, Tracy. Well, the real answer is 10 cents is what it would cost to keep this incredible mission going. So if you want to pass that along to friends and family and senators and Congress people, please do so. And with that, any questions? Also, by the way, life.
Thank you, Tom. All right, let's get this going. Reminder, text that number on the screen. It's me, if you have any questions. If Juno was operational when Europa Clipper arrives, is there any opportunity for dual observations?
Yeah, absolutely. That would be fantastic. And so that would be very scientifically valuable.
How has NASA or the Europa Clipper team accounted for human-centric ideas of life?
Human-centric ideas of life. Yeah, that's an interesting one. It's hard to get away from the fact that we only know one example of life. People are definitely thinking about the possibilities, the conditions for life to exist are really very much based on the examples that we have on Earth. There are definitely people thinking about other chemistries like non-DNA based life, that sort of thing. But I think in terms of how Europa Clipper is going to investigate whether or not Europa is habitable to life, it's really still based on our idea of life.
Yeah. How predictable are the plume eruptions on Europa? Can they be forecast enough to fly an orbiter through an eruption to gather data on the contents of the plume, compare them to later surface samples,
So
etc.?
that's a really interesting question. So we think we've seen some evidence of plumes being erupted on Europa, but when we went back to look again with the Hubble Space Telescope, we didn't see anything. And so some people don't believe the plumes exist. I'm not as skeptical, but I think if they do exist, they might be very variable. So it might be harder to predict. Then, for example, Saturn's moon Enceladus has also a huge plume, and that's been very constant throughout the last 20 years or so. If Europa has plumes, they're probably very variable and sporadic.
How do we study how radiation affects Europa? Can labs simulate that level of lethal radiation?
Yeah, so we use a mix of lab experiments, some of which are carried out just down the road at Swery. We also use computer models. We use measurements of the radiation environment by spacecraft like Juno to inform our modeling in our experiments. So, yeah.
Off the top of your head, what major challenges do you think a lander would face?
Congress.
And we'll leave it at that. All right, we'll close with a fun one. Do you have a favorite possible alien life form that could be found at Europa?
I would really I like to think big. I'm thinking about some sort of massive monster squid, maybe like a kraken kind of thing. That's what I'd like to find.
Yeah. All right, let's give it a round for our speaker, everybody. All right, and with that, we'll take a 5-minute break, a loose 5. We'll be back at 7:35. Yeah. Don't crowd the bar, please. That's the only note. All right, everybody. Find a stopping point in your conversation. Let's find our seats. Let's bring attention back to the front. It is time for our monthly installment of Astronomy in the News. Usually it's Caleb, but since he's doing double time, I'm doing the stories, he's doing the sky, because he's the best one to talk about that. Yeah, colliding galaxy clusters and more. We'll see more about that here in a second. Caleb, what's up in the sky?
Yep. All right, so here's our sky in June section for what's coming up over the next few weeks. So first and foremost, we are now getting very close to being officially in the summer season. Somewhere there around about June 21st or so, we will be in summer, and therefore right now, when you go outside, you are looking at a sky that is partially a springtime sky, partially a summertime sky. So go out about 10 o'clock p.m. This is about mid-month. It's going to shift a little bit, for exactly right now. But if you look over here toward the west, you will see a lot of the constellations of spring setting toward the western horizon. Find the Big Dipper up there in the sky, more appropriately part of the constellation of Ursa Major. Follow the arc of the Dipper, or the tail of the bear, to Arcturus, part of Boötes, the herdsman, and then spike down to Spica, which is part of Virgo, right there in the sky. Follow the front two stars of the Dipper on down to Regulus, that bright white-ish colored star there in the sky. And you find this kind of backwards question mark shape that marks the head, the mane, the chest, and then Regulus, the heart of Leo the lion, and then this little triangle shape back in marks the back half of Leo. So again, over toward the western half of the sky, all of that springtime stuff. Now, if you look for Regulus right now, very near Regulus will be a distinct red-colored star-like object that, if it is sufficiently high enough in the sky, will not twinkle like the other stars nearby. That is the planet Mars. Make sure to get a good look at Mars right now, because it will get lower and lower in the sky as the summer goes on, and it will become more difficult to see. We will also get farther away from it, so if you're looking at it through a telescope, you will see less and less detail as time goes on. So get your look at Mars now while you still can. But the real treat, especially down here in the state of Texas, where the stars at night are big and bright, are a few southern sky objects that, if you go much farther north than the middle part of Texas, you start not being able to see. They are the globular cluster Omega Centauri and the galaxy Centaurus A. Absolutely beautiful objects, particularly in the case of Omega Centauri. Look down here in the south at this time of the evening. Find the constellation of Centaurus. It's this funny Y-shaped thing. Use a pair of binoculars, and you will find just below the kind of right-hand arm of that Y there, the globular cluster Omega Centauri. Very distinct object. Make sure to look at that. Again, dark sky. You want a very dark sky, clear, unobstructed horizon. And then just above that, there will be a fainter spot of light. That is that distant galaxy Centaurus A. We are still waiting on the nova explosion T Corona Borealis. So find Boötes there in the sky. Find that kind of cup-shaped constellation there, if you will. And then just off to the side of that is where eventually, sometime in the next few months maybe, there will be what appears to be a new star show up there. And that is a star that actually is in a binary system, close interacting binary system, that will brighten tremendously. Bright enough to be about the brightness of that little star right there, just so you know. Now wait until early in the morning, 4 to 5 in the morning. And at that time, you're going to get this nice parade of planets in front of you over toward the eastern side of the sky. So everything in the sky shifts. You start getting all this nice Milky Way stuff straight overhead. But over here in the east, you will find Saturn and Venus over in the east. Venus will be very distinct. It is very hard to miss, extremely bright. And if you're around the 19th or 22nd, the moon will kind of find its way between these two planets. If you're on the 19th, it'll be right next to Saturn. It will be a waning, almost crescent phase moon. And then going toward Venus on the 22nd, you'll be very nearby. And that is the sky in June. So make sure you get a good look at all of that. And Aaron, go ahead and take away with the news stories.
Yep.
Thank you.
Got a little wrapped up. Strange star at radio frequencies found to be just as strange in X-rays. Chandra X-ray Observatory and Australian Square Kilometre Array. What? Yeah, Chandra. But anyways, observations combined from Chandra and radio array in Australia to observe phone number. Long period radio transient known to vary in radio every 44 minutes, also shown in X-rays. So this class, this long period radio transient was discovered in 2022, and they've found, I think, only like literally 2 or 3 or 4. This is one of them. This is the first time, I believe, it was found also to have X-ray emission. And these are very different from pulsars. Pulsars are like microsecond pulses. This is 44 minutes, so thousands, if not millions times longer, which is very weird. My favorite of the month, JWST shows Jupiter aurora in stunning detail, reveals odd mystery. The aurora have regions visible in IR, that's observable by JWST, but not visible in the UV. They did observations at the same time, simultaneous observations. The brightest IR observations were not visible in UV and vice versa, which perplexed the astronomers very much so. And so this animation that's going up on here, it's about, I think, almost 2 hours. Almost 2 hours. And you can actually see like the undulations in the aurora and like the movement of the aurora. That's pretty trippy. Jupiter's very far, like 5 times as far as us. That's really cool. We can barely see our own aurora. And then we can see the ones on Jupiter. So that's really cool. I've watched that video, I don't even know how many times. Every time it pops up on my phone, I'm just like, yeah, gotta watch it again. And then Chandra reveals galaxy clusters radiating for another impact. First collision of galaxy phone number 2.8 billion light years away happened nearly 1 billion years ago. So the red are the shock fronts, and then I don't know how. I tried to read the article to understand how, but somehow the astronomers inferred that because of the shock fronts, they deduced that they're on their way back in towards each other, so they're probably going to collide, way down in the future. But yeah, it's like one of the first deductions, I guess you could say, that the galaxies are going to collide again, which is pretty cool. And then, Caleb made all these slides, and I'm doing it because he's doing double time. So, Caleb, want to tell the people what's going on?
Yeah, certainly. So, okay, upcoming events that you should know about astronomy related. So, first of all, UTSA Observatory / San Antonio League of Sidewalk Astronomers related events. There will be a observing at South Yona River State Park probably on June 28th, that Saturday. Go out there, join us for observing. It's a really fantastic time. Ask me for more information about it. I'll tell you everything you need to know. Really dark skies. Yes, we will be able to see Omega Centauri and Centaurus A out there, as I was talking about, by the way. A really great time, so make sure you get a good look at that. And then every Friday at 8 p.m., more on the west side out there, Uvalde County Visitor Center in Conkin, Texas. We're actually going to be doing a series of observings out there throughout the summer. So in June, every Friday night out there at 8 p.m., we'll be out there set up and observing out there. So that'll be really awesome if you get the chance to go. Kind of a fun little spot, too. There's a little ice cream stand nearby there and everything. It's just really fun, summertime vibe. And then San Antonio Astronomical Association, every Wednesday at sunset, they do Observing Out Raymond Rimkus Park. And then they have a whopping 4 events coming up on various Saturdays throughout the month, June 7th, 14th, 21st, 28th. I'll let you read those locations. And by the way, you can find their information online on their website. Just look up on Google San Antonio Astronomical Association, and that information is there. And then Scobie Planetarium, they have planetarium shows on the 6th, 13th, 20th, and 27th. Basically, every Friday of this month, go there, they have planetarium shows, and if I remember right, usually they do have observing there on the evenings when it's clear as well on those Fridays. So make sure to keep those events in mind. And we have, there. Yes, we have a couple of images to wrap up. Always one more thing. So, first, that nice, beautiful image of Sombrero Galaxy from the JWST. Please go online, take a look at that image. And then one that I found very intriguing, this image of Mars over on the right-hand side here. That image of Mars is kind of grainy looking. It's because it's under low light. They had to do a lot of increasing the gain on the image to get the detail. But that little bright spot of light there, just a little off-center and up in the image, that's one of Mars's moons. That's Deimos, as it appears in the skies of Mars. Okay, and I think we'll go on to the talk part. So, Erica, go ahead.
Yeah, all right. So, I have the distinct pleasure, Caleb, take that, of introducing my fellow graduate student in the UTSA program. He is also part of the UTSA SWERI contingent of our program, hailing from the lovely central Kansas, which he does not shut up about, but we'll not talk about that. I am happy to introduce my favorite Carl Sagan impersonator, Caleb Gimar.
Well, I'll make sure tonight to tell you about all of the billions and billions of possibilities. Okay, anyway. Oh. Thank you for making me look a lot better than what I actually am. Okay. Oh, drinking word, yes. Satellite. We'll go with satellite for the drinking word this evening. Okay. All right, so, Surveyor, Battle of the Moonbound Machines. Why on earth did I decide to talk about this tonight? Well, one, I was asked to do this talk with very short notice and already had this prepared partially. But number two, it just so happens that exactly 59 years ago, as of the beginning of this week, is the date that Surveyor 1 landed on the surface of the moon. So we are on the 59th anniversary of that. Yeah, I know, I wish it would have been next year, so it would have been 60 exactly, but yeah, you can't ask for everything, you know? So first of all, before Surveyor, before the space age, before that year in the late 50s when we started venturing out away from the Earth, this was our view of the moon. It tells quite a bit about the moon. It's what you can see outside when you look at it through a telescope. You can definitely see that there's some very interesting geologic features, the craters that are there. If you zoom in really closely, for instance, at the region right here, you see the Apennine Mountains, the Caucasus Mountains, all those really nice geological features on the moon. However, you can't really tell much without going there. Did the moon form with the Earth? Was it captured? Those mountain ranges are the result of, normal geologic processes involving plate tectonics. Certainly not a lot going on there now. It seems pretty dead. There's all of these different questions that one could ask about the lunar surface just looking at the moon. And so to solve many of these mysteries, we would have to actually send something to the lunar surface. Now, just before we started actually seriously sending spacecraft, satellites mainly I should say, to the moon, our largest satellite, natural one at least, there were a number of ideas of what the surface of the moon would be like. So you go there And you had a lot of people looking at the moon, of course there's telescopes, and seeing these mountain ranges and various chasms on the surface of the moon, thinking, well, this is going to be this really jagged terrain with all these tall mountains and things like that. And so many renderings of what the moon's surface would look like pre, 1960s era had this kind of a terrain. This is a painting by Chesley Bonestell, very famous space artist, actually. He was commissioned to do a series of extremely influential paintings for a series of magazine articles in the early 1950s called Man Will Conquer Space Soon. And he had this vision of this really kind of foreboding place with all these tall mountains that produce these great shadows on the surface and everything. And of course, the astronauts that would eventually go there would have to work around all of this, as you see here. So that's one vision. But that vision assumed something. That vision assumed that a lot of those geologic features that you see on the surface of the moon, including the craters, were largely due to volcanism at some point in the ancient history of the moon. It completely ignored the role of impactors. In fact, it was really unclear as to if impact events formed a lot of these geologic features, as it so happened to be really the case. So then you had another vision, when it became clear that impact events could actually make many of the craters and other features in the moon. You had the idea that perhaps the lunar surface wasn't this really rocky, dead place. Maybe it was some place where there had been, over the eons, just a constant depositing of dusty material. And so one scientist, Thomas Gold, who was at Cornell University, and someone mentioned Carl Sagan earlier, you can thank Thomas Gold for hiring Carl Sagan there at Cornell, had a rather unconventional idea for the time. He thought that after eons of bombardment of the lunar surface, that there would be this extremely thick layer of loosely held together dust on the surface of the moon, the regolith as we call it now. But of course, it isn't very thick. It's only, a few centimeters thick. You can walk on the lunar surface without sinking into it. But he thought that the moon would have this kind of cotton candy quicksand-like constituency, as I call it, where after all these impact events, these fragments would be static electrically charged, and they would kind of stack up on top of each other really lightly, and so anything that landed on the surface would get sucked down into the soil of the moon, basically. Sounds fun, doesn't it? Well, he eventually revised his calculations, but he never really gave up on the idea that there would be this very loosely packed lunar soil. And so he insisted when the Apollo astronauts went to the moon that they carry this camera with them. It was called the Gold camera, and it was a stereoscopic imager. And it actually allowed the astronauts to take these images. It's carried on Apollo 11, 12, and 14. It'd take these close-up stereoscopic images of the lunar surface. And even though he didn't necessarily find this really thick layer of kind of loosely held together soil structure, he did find these fairy castle structures that had been predicted on the lunar surface, these very loosely held together structures from so long of the lunar regolith building up and being statically electrically charged as he had predicted. But nonetheless, though, before all of this, you still had to answer the question, which picture was right? The rocky moon surface or the dusty moon surface? Well, this took a whole new urgency by the late 1950s. Beforehand, there's a number of people working on satellite programs. And an announcement's made in 1957 that there would be a series of satellite projects launched for what was called the International Geophysical Year. And both the United States and the Soviet Union made announcements of this form. And so the first to the punch were, of course, the Soviets with Sputnik 1 on October 4th, 1957. Now, the common history is that everybody in the United States just absolutely panicked about this, but that isn't completely true. Within Russia itself, Sputnik 1 wasn't looked at as that big of a deal, because this wasn't the satellite that they had originally wanted to launch. They actually had a larger satellite that was originally planned. However, they had to delay that and go with the simpler satellite. They launch this, and okay, fine, expected. But then the next shock takes place. Sputnik 2. And this is where there's a big outcry. Sputnik 2 actually carries a living being, this dog Laika, who unfortunately probably perished very early in the flight. The Russians covered up the fact that the dog probably did not live that long in the spacecraft, but nonetheless, so it was a demonstration that they could launch a fairly complicated spacecraft into space, and a fairly massive one at that. And that's where there was a lot of panicking here in the United States. And it becomes part of the larger Cold War power struggle of the time. And so our leaders at that time, Eisenhower in particular, start wondering, how can we possibly get ahead of the Russians in the space race? Well, the immediate answer is, let's send something to the moon. Okay, well, in order to send something to the moon, you have to develop a spacecraft capable of doing this kind of a mission, that electronic systems that can actually operate in such an environment, the autonomous control systems to make sure the thing doesn't just go completely out of whack on the way. So it's a little too much to think about at this early of a stage when our satellite programs are very primitive. So there is a very nascent early idea given, maybe not a landing probe, maybe not even a spacecraft that can actually do any science in detail. Maybe the best idea is to send a nuclear weapon to the surface of the moon, detonate it, and see what happens. What could possibly go wrong? There actually was a proposal at this time called Project A119 to send a small nuclear detonator to the surface of the moon, and you would be able to see the flash from the explosion through a telescope here on the Earth, and you'd be able to get some idea of the surface properties of the moon just from that long of a distance. Thank goodness they did not actually go with this primitive of an idea. They wound up going ahead with a program to make a working lunar probe. Now, this was a big challenge at this time, and unfortunately, we were beaten before we even began, really. You had Luna 1, which passed within 726 miles of the moon on 4 January 1959, Soviet probe. Now, this one was actually supposed to impact the moon, but they covered that up. They said it was only a flyby. And then Luna 2, which impacted the moon on 14 September 1959, so that one actually did impact. And then Luna 3, which passed by the moon and gave us our first images of the lunar far side. And you get the question in your mind, can they possibly fail? The answer to that question is yes, and so did we a lot. Before Luna 1, the Soviets actually tried 3 separate attempts to do one of these lunar impactor missions, and each of them failed for various reasons. Luna 1, again, didn't actually impact. It was on the wrong trajectory. It just flew by. So they actually had a lot of failures. The difference is they just didn't tell anyone about them. We went ahead and told everyone about our failures. In fact, we broadcast a lot of it live on television for everyone to see. And so if you attended a launch at the Cape back in the late 50s and early 60s, about 40% of the time, it was okay. You'd see something like this. A first successful American satellite launch, Explorer 1, January 31st, 1958. Great launch, perfectly functional. And then the other 60% of the time, yeah, something that looked like that. Vanguard TV3. This is our first attempt at an Earth orbiting satellite, actually. December 6, 1957. So the rocket technology of the time was very finicky. So you're looking at going to the moon, sending some kind of a spacecraft to the lunar surface with technology that's only working about 40% of the time. That is a big gamble. But nonetheless, we went ahead and pursued this, NASA did. And the first program to try this was a program called Ranger, and this had the same goal that the early Luna probes did, just impact the surface of the moon. It carried a series of scientific instruments to measure particles and fields, cameras to image the moon on the way toward the moon. So, simple enough. Send up the spacecraft, send it on a trajectory to the moon, impact moon. Sounds easy, right? Yeah, didn't necessarily work that way. So the first Ranger probe, the Agena booster that carried the spacecraft to the moon, failed. Second one, failure. Now, in each of these cases, the objective of the mission was not necessarily to reach the moon. It was merely to go on a trajectory that would have taken it very near the moon and sent back particle and field data in space. Okay, no big deal. You know, we had a couple of failures early on. Ranger 3 is the first one with the actual intention of going to the moon, and it had a guidance and programming error. Basically, something didn't happen right in the way that the computer in the spacecraft communicated with the ground and vice versa. Similar kind of failure for Ranger 4, although in the case of Ranger 4, it passes. And then when it passes the moon, it actually is entering into a trajectory where it impacts the far side of the moon. No communication, no data, but hey, you know what? At least we've impacted the far side of the moon. First people to do it, accidentally. And then Ranger 5, there's a power failure on that particular spacecraft. This power failure very likely could have been caused by a frying of the electronics in the spacecraft by the sterilization procedure that was used for these spacecraft. They heated them to very high temperature to kill any microbes. And so at this point, Congress starts asking questions. You have launched 5 probes to the moon. None of them have worked. What is the matter with this program? So they take a little bit of time to regroup. It was JPL leading this project. The mission managers there at JPL regroup, and they tried to launch Ranger 6. Now, one thing they determined is they've tried too hard on these past few. They put on too many instruments. They've made the project too complicated. So we're going to just put a television camera only. No other scientific instruments, just a television camera on board Ranger 6. Well, Ranger 6 goes up, everything works except the camera. Yes, they send us up, and the camera shorts out on them. It impacted the moon successfully, but no pictures. Darn, that's too bad. Finally, with Ranger 7, everything works out well, and it becomes the first United States spacecraft to successfully impact the surface of the moon and send back data of the lunar surface on the way toward the moon. So that was on July 31st, 1964. It was a long time coming. That's quite a while after those early Soviet flights during the 1959 time frame. So now we go to the next step. Land on the moon. And this is where the Surveyor program begins. So Surveyor is the first United States program to actually soft land rather than impact and intentionally crash land on the moon, to soft land on the surface of the moon. 1966 to 1968, it requires a whole new kind of spacecraft and a whole new kind of rocket to accomplish the job. So we'll first start with the rocket, the Atlas Centaur. Now the Atlas itself, the first, it's actually technically first and a half stage of the rocket, had already been used many times for space flights. The Atlas rocket itself was used to launch the first few Americans into orbit around the Earth. John Glenn, Scott Carpenter, Wally Schirra, and Gordon Cooper all orbited the Earth in Mercury spacecraft. They were carried by Atlas rockets. It was a very complex system. This early ICBM, as it was actually militarily used, was designed to be as light as possible, so it used what were called balloon tanks, where the evaporating fuels is used cryogenic oxidizer in the first stage, liquid oxygen, where basically the pressure of that evaporating gas would maintain the structure of the rocket. So if you did not have the rocket pressurized with compressed nitrogen or fueled up, it would collapse in on itself. It was a really remarkable system. But what was unique about the Surveyor rockets was the upper stage, the Centaur stage. No rocket designed beforehand, meant to launch our previous satellites. I kind of gave you a break on that there for a while, didn't I? Yep. No other rocket designed to launch our satellites at that point used liquid oxygen and liquid hydrogen as a fuel. The Centaur upper stage was the first stage used in spaceflight to do that, enabled by these RL-10 engines. They were manufactured by Pratt & Whitney at the time. That general design is still in use today. Aerojet Rocketdyne now manufactures them, but they're somewhere in the neighborhood of about 12 to 15,000 pound. Actually, no, take that back. Sorry, about a 23 to 24,000 pound thrust engine each. So roughly about 50,000 pounds thrust for the entire upper stage. The Atlas rocket itself, the lower stage, had about 380,000 pounds thrust for these particular launches. So you need a capable launcher like this in order to launch a heavier spacecraft on a translunar trajectory. Why do you have a heavier spacecraft? Well, unlike just shooting something at the moon in an impactor, you have to carry enough fuel in a stage in order to slow down and be able to maneuver so you can enter on the proper trajectory to the lunar surface and slow down, of course, without crashing, if you will. And then the different kind of spacecraft. Now, this is what's really remarkable for the time. Almost all aerospace engineering done before these early satellite and space probe programs was done with the intention of sending something eventually through the Earth's atmosphere or within the Earth's atmosphere. So again, very much aero part of aerospace engineering. But this is a very different kind of very different kind of craft, in particular a spacecraft. It has to be able to work in the 1/6 gravity environment of the moon. It has to be able to work on limited power. In the case of this Surveyor probe, it was only 85 watts. Take one of those old light bulbs, old incandescent light bulbs, you screw it into the ceiling, that's about 85 watts. That's all the power that was available in this system. So you have to be able to operate, and by the way, this is before they have microchip-enabled electronics. This is during the days of the early transistorized electronics. So you have to be able to operate all of these systems on 85 watts. And then, of course, autonomous operation. Again, this is before modern computing systems, and you have to build a spacecraft that can, largely without input from the ground, be able to go through each of the flight processes, start engines, stop engines, stage, deploy landing gear. All of these different systems have to be at least semi-autonomous in order for this to work. It is an extremely different kind of engineering. So of course you launch toward the moon, you're launching at somewhere in just basically over the 17,000, 18,000 mile per hour mark. Once this probe reaches the moon, it has to slow down from 6,100 miles per hour all the way down to 240 miles per hour, and then just a few feet above the lunar surface to 3.5 miles per hour, and then touch down once coming off the engine. It speeds up a little bit to 10 miles per hour. And by the way, they have to engineer a landing pad system with no knowledge of what the consistency of the lunar surface is. Big job for 1964. So one of the main goals, of course, is to be able to get up-close imagery of the lunar surface. Surveyor 1 really only carried this scientific instrument. This was a camera. The camera was a Vidicon television tube-based camera. Now, what on earth does this mean? Well, today, of course, in our pockets, we have all of these nice CCD cameras. They didn't have CCDs back then. What they had was a tube-based camera that had a phosphor on the end of the camera that would, of course, illuminate when light hit the phosphor. And then there was a cathode behind that phosphor, photocathode behind that phosphor, that would have a voltage applied to it. And when a kind of describing it's a little, I'd have to go into a lot of detail, but nonetheless, when a photon strikes the photocathode, there's electrons produced, and it'd strike this grid, and as the electric signal went through and gained the signal of that electron striking the grid, that would be replicated on a television readout when broadcast to the ground. It was very low resolution. Basically, the highest resolution images in practice were about 600 lines. Yes, they didn't call anything a pixel back then. It was called a line. So about 600 lines. So that's only 600 pixels in one direction. A few more, a few less than that in the other direction. Very low resolution imagery, but it's what they had in those years. And you have very limited bandwidth in order to broadcast these images. There was only about 200 kilohertz available bandwidth to broadcast these images to the Earth. So it's very slow scan, extremely primitive technology compared to today, but nonetheless it worked. This was a principal scientist for that instrument, Eugene Shoemaker. He worked for the U.S. Geological Survey back in the 1950s, and he was one of the first geologists to really grasp the importance of impact processes on bodies in space, including our Earth and our largest satellite, natural satellite, the Moon. Yep, so very important contributions to the field, and he was the principal investigator for the camera system. Also, he was an advisor to the Apollo program in terms of training the astronauts for what they would encounter on the lunar surface in terms of the field geology aspects. And he might have actually been one of the early scientist astronauts, like Harrison Schmitt eventually was, who eventually walked on the moon in Apollo 17. But unfortunately, a health issue prevented him from being selected for that program. But nonetheless, though, he made many contributions to the program. Eventually, in the 90s, he actually helped with observations of a comet that eventually became known as Shoemaker-Levy 9 that impacted Jupiter during the 90s. Look up more of that story. It's really fascinating. I'm not going to go into all the details of it this evening. This camera was capable of doing color, but in a very interesting way. It actually had a little color wheel inside of it that would shift between red, green, and blue filters. And then that mirror system there allowed the camera to be imaging at different altitudes. So in other words, you could tilt the camera down some in order to get the ground in front of the spacecraft, or out some in order to get the far terrain in front of you. That, by the way, is the actual camera from Surveyor 3. I'll tell you more about how that was obtained toward the end of the talk. Now, we were beaten again, though. Yeah. Luna 9. So Luna 9 was the first successful Soviet attempt at landing on the surface of the moon. It even produced these images. So first soft landing, first images from the lunar surface, landed 3rd February 1966. However, at this stage of the space race, it was neck and neck. So we followed up with Surveyor 1. So Surveyor 1 launches on May 30th, 1966, and lands on June 2nd, 1966, and works perfectly. It is absolutely one of the most remarkable feats of the early space race. Not only did we send back black and white imagery, but that camera on board was able to send back, color imagery, as I mentioned. So that's actually the first color image of the lunar surface. And that color imagery actually is very informative. It can tell you the color shade of the lunar soils that are present, including some that happen to be on the landing pad there. And that can give you a little idea of the composition of what you're looking at, roughly, with some other context. Now, Surveyor 1 was followed up by other missions. The Surveyor program as a whole sent 7 probes to the moon. Each of these probes landed in slightly different locations on the lunar surface. 2 of them did not function, Surveyor 2 and Surveyor 4, but 3, 5, 6, and 7 did, and each of them furthered the development of the spacecraft and lunar science in their own individual ways. So first of all, later missions would carry more scientific payloads. Again, Surveyor 1 only had the camera. Surveyor 3 included this geotechnical scoop right here. It's geotechnical arm and scoop assembly that you see in these images here. Now you're probably wondering, is that going to take that soil and analyze anything? No. All that scoop did was scoop through the surface soil in order to find what the consistency of the surface soil was and be able to dig a little beneath the surface, see if there was any change in the material that was present at the upper layer and lower layer. Generally, it did help out, though, along with, of course, imaging the footprint of landing pads in determining what the consistency of the lunar surface soil was, finding that you didn't have the cotton candy quicksand moon, but you did have that very fine layer of regolith, as we call it, across the lunar surface. You can take the images from that camera, and again, they were very low resolution square images, again, 600 lines for one mode. I think it was only 200 lines for another mode. And you can stitch them together in these large panoramas. And then some of the later missions also had this particular instrument right here. That is an alpha scattering experiment is what that is. So it's, again, a very simple way, well, maybe not all that simple, but simpler in comparison to what we use today, a way of understanding the composition of the lunar surface. This alpha scattering experiment had a small radioactive source inside of it. It was made of cesium. And that cesium source would, of course, propel alpha particles, would emit alpha particles to the lunar surface. And there were a series of radiation detection instruments on each side of the source inside of the box that you see here. And when the alpha particles would scatter off the lunar soil, either one or two things would happen. You get a direct scattering of the alpha particles, which, by the way, are stray helium nuclei, to get an idea of what this is in your head. Or they would interact with the lunar surface soil, and there would be other kinds of radiation, mainly proton radiation, emitted away from the surface. Also some X-rays, too, possibly, emitted away from the surface material. So you had both kinds of detectors in there to detect either scattered alpha particles or the protons and other things scattered away from the surface. And using this alpha scattering experiment, the scientists that operated it were able to determine that much of the material they were looking at was basalt material. They saw a lot of silicon in the signature, a lot of oxygen in the signature, and a good amount of iron. They were also aided in that iron determination by a few magnets that were fixed to the sides of the spacecraft that could very lightly attract any iron-containing minerals. So they were able to use this instrument to determine that most of the material that they were looking at was basaltic, and therefore originated, of course, during the ancient history of the moon in these large lava plains that we now call the or had called and now understand to be the Maria, or again, the actual dried-out lava plains. Dried out's kind of a bad term, but I'll use it. So again, key accomplishments. First, color imagery of the lunar surface, Surveyor 1. Establishment of preliminary geotechnical properties of lunar regolith, Surveyor 1 and 3. Confirmation of basaltic composition of the Mare soils, Surveyor 5. First, mobility of a robotic spacecraft on the lunar surface, Surveyor 6. You see that little thruster there? That's the that's the type of vernier thruster that was used on the Surveyor spacecraft. It was a rather innovative little engine for its time. It used hypergolic fuels, meaning the fuels ignited on contact. It could run for a few minutes, produce about 100 pounds of thrust, and it was restartable. So on Surveyor 6, the operators actually tried something rather bold. They started these vernier thrusters, high thrust, for enough period of time to make the lander hop on the lunar surface about 8 feet. Yep. This was the first incident of actually maneuvering a robotic spacecraft on the surface of an extraterrestrial body. Yep. And then finally on Surveyor 7, which, by the way, Surveyor 7 was the only one to carry all of the scientific instruments, the camera, the scooping system, the alpha scattering experiment. It's the only one that carried all experiments at the same time. There was a laser communications test done, very crude one. They didn't actually really communicate using the laser radiation, but they did try to see if the spacecraft camera could observe laser beams being emitted from a laser source here on the Earth, and of course being able to be observed at the lunar surface. And this is this image here. So this is from Surveyor 7. And you can actually see these two little marks here, okay? Those two little marks are laser beams being beamed towards the spacecraft from Kitt Peak Observatory in Arizona and another location in California. Yep, so a very early nascent test of the concept of laser communications in space. So the epilogue. Apollo 12, one of the goals of that mission was to do pinpoint landing, meaning the astronauts would have to navigate to a predetermined exact spot on the lunar surface. It was determined that maybe the best target to do this was one of these Surveyor probes that had landed there previously. So Surveyor 3, the one that was the first to carry that scooping array right there, it arrived at the moon back during 1967. If I remember right, it was sometime in that April 67 time frame, but you can double check that just to make sure. Apollo 12 was launched in November of 1969. The probe has stopped operating by this point. The Apollo astronauts figure out on this mission, that was Pete Conrad as the commander and Alan Bean as the lunar module pilot. They figure out that you can take a look at the imagery of the landing region, really examine it, they did this before they left, and try and follow the craters and other marked features on the surface of the moon to roughly where the lander is. They used this method, and they were able to land just, a few, probably just maybe about 100 meters away. I'd have to look up the exact number, but not very far away from the lander there. They get it right on the mark, essentially, close enough to where they can walk over to the spacecraft. Bean and Conrad and Bean, they go ahead and they collect parts from the Surveyor 3 lander. They collect that camera, which is now on display at the National Air and Space Museum in Washington, D.C., and they collect parts of the scooping arm as well and a few of the struts from the spacecraft. So they analyze it. Now there's an early idea that maybe some microbes from the Earth that attached themselves to the camera and other parts survived on this probe on the lunar surface. The problem is, looking back at the imagery of how these pieces were handled when they were returned to Earth, they did not do a very good job of social distancing from the parts or wearing masks or anything like that around these components. So probably the microbes that they found were detected from post-flight contamination. But nonetheless, so they did actually take that camera, they plugged in the camera on the ground, the camera still operated, they took a look at that scoop, they found that there was just minor paint fading on the scoop, and basically what they figured out was something can survive for a long period of time in space and still generally operate. And this was, of course, able to inform projects like Voyager later on that would require long-term operation of spacecraft and satellites in Earth orbit as well, by the way, for an extended period of time. Now, after the mission, though, cameras distributed to the Smithsonian. What about the scoop? Yeah, what did happen to the scoop? The scoop was a little bit of a mystery for a number of years until a museum CEO named Max Airy, who led the Kansas Cosmosphere and Space Center back in the mid-90s, happened to visit JPL, and he was really interested in this scoop. He wanted to find it and put it on display. And the systems that he had kept telling him, it was destroyed in testing a long time ago. Well, he happens to be there, and he asks one of the technicians at JPL, listen, I wonder about this scoop. Records show it last ended up here. People are saying it was destroyed. Where is it? Apparently, this technician that he's talking to takes him into a back room, opens a safe, pulls out a bag that has a scoop in it, and says, this isn't supposed to exist. There's quite a bit of back and forth between Airy and NASA about whether the scoop even actually does exist and if he can have it. Eventually it settled out, and half of the scoop is on display at the Cosmosphere, as it's called now. No Kansas part of it, but just Cosmosphere up in Hutchinson, Kansas. The other half is on display at JPL. And then also in that museum in Kansas, there's that backup unit. It's actually an engineering unit that the engineers at JPL modified to look like Surveyor 7 on display there. I worked alongside these things for about 10 years. It was really awesome to be able to go and see these artifacts. Get a chance to go up there and see them yourself. All right. Also go to JPL, I think, in the visitor center there. You can see the other half of that scoop. And go to the Smithsonian, where they have the camera on display and the other such parts. So I'm going to wrap up this talk with a video, a short video, that describes the landing of Surveyor 1, and we'll see if we can, yeah, you can get this to work. No sound? Not yet? You might want to check and make sure that you don't have the computer itself on mute. No sound? You know what, if you can't quite get the sound, I can verbally describe what's in the video. Yeah, I know that, yeah. Okay, don't do that, because you're going, if it does turn on, you're going to blast the speakers to, yeah. Come on.
Liftoff plus 4 minutes and 3 seconds.
There we go. Okay. Roll it back.
Shown by the animated diagrams in the monitor, the Atlas Centaur. All systems are reported in excellent condition at this time.
Pressurization. Go, Atlas. Go, Centaur. Atlas autopilot. Go. Centaur autopilot. Go. Launch director. Go.
Gas looks good. Doppler readout is nominal. Chamber pressure looks good. Liftoff was at 7:41 Pacific Daylight Time on an azimuth of 102 degrees. The aerodynamic shroud is off and Grand Bahama is tracking. Liftoff plus 4 minutes and 3 seconds. As shown by the animated diagrams in the monitor, the Atlas Centaur separation has occurred. Centaur cutoff. Surveyor is injected on its lunar flight path. Separation. And report that the landing legs are extended. The Surveyor is now in space.
"63 hours after launch, Surveyor 1 was only 1,000 miles away from the moon, with the speed increasing as the moon's gravitational attraction beckoned.
Vernier ignition. Retro is now firing. Ignition looks stable. Falling steadily. 63,000 feet, 3,500 miles an hour. Now at 30,000 feet. Retro burnout confirmed.
The vehicle is supposed to enter a fixed rate of descent. So that happens.
28,000 feet, 425 feet per second, 24,000 feet. Falling steadily. Down to 12,000 feet. 10,000, all signals normal. Surveyor reported in excellent condition, all signals good. 1,000 foot mark. 800 feet. 600. 400 feet. 200 feet. 100 feet, 13 feet per second speed.
A certain distance above the surface, the engines are all supposed to shut off. And then it's supposed to drop to the surface. And the engines all shut off. It worked. We're down. It's still transmitting.
Surveyor 1 touched down at 5 miles per hour, a mere 1 second off the intended landing time. For the first time, an American spacecraft had achieved a soft landing on another celestial body. Surveyor 1 operated for 6 weeks, surprising engineers by surviving a bitter cold lunar night. In all, the sturdy lander sent back more than 11,000 images before its batteries ceased to work. Surveyor 1 now rests where it landed in 1966, telling us of its presence by casting a silent but long shadow on the lunar surface. 6 more surveyors were launched over the next 2 years, providing a treasure trove of science about the moon. Although 2 of the missions would fail, the increasing ratio of success to failure demonstrated that JPL was clearly learning from its past mistakes. And NASA had the answer to its question. The lunar surface was solid and suitable for landing by the Apollo astronauts.
And that's the story of Surveyor 1 and the rest of the program, and basically how we learned to go to the moon. So I'll now take any questions that anyone has. Thank you.
Thank you, Caleb. I've said it once and I'll say it again. All roads lead to Hutchinson, Kansas, apparently. I admire, I respect your ability to throw in Hutchinson, Kansas at any opportunity you get in front of a public audience. It is remarkable. It is honestly. All right.
It was a little hard to do on that one, I mean, you know.
That didn't seem that hard. That seemed right there.
Yeah. No, a little hard not to do.
Oh, yeah. All right, first question. Was your past life a Surveyor mission member? You seem to know a lot about Surveyor. Was your past life a Surveyor mission member? You seem to know a lot about Surveyor.
No, I first of all, I'll tell you the story of that presentation. So again, that Space Museum I mentioned at the end there, I worked there as an educator for 10 years. And basically, we'd have the lighter version of this event every month. We would have this third Thursday event where they would do a breakfast. Yeah, I know. So, breakfast? I mean, why not evening with the beer and everything? I mean, come on, you know. But no, we would do this breakfast thing. And of course, the only people who wake up for breakfast are largely retired folks and everything, you know, coming in and everything. So, you know, it was a certain audience that came and watched this. But we would have this series of talks, and the 50th anniversary was coming up for Surveyor 1 in 2016. And I found this all interesting anyway. I had read about a lot of it many times, but I never read about it in a huge amount of detail. And so the education director there at the Cosmosphere tells me, and this was his voice, "Caleb, we have one of these events coming up. Would you like to do a presentation about Surveyor 1? And I said, yeah, sure, I'll go ahead and do a presentation about Surveyor 1 and everything. So I went ahead and I sat down and really researched this program, and I found all this really fascinating information about how the systems work, the amount of effort that was put into it, just all kinds of different little facets and everything that were so fascinating. So yeah, that's kind of why. And then also, that engineering unit that I mentioned, it was right outside the door of the planetarium, so I knew a lot about it, so that if visitors came up to me when I was standing outside the door before I'd put on a show asking about it, I'd be able to reel off some things about the spacecraft, so, yeah.
So it was kind of mentioned a little bit towards the end in that video, but so was Surveyor designed with Apollo in mind? Or did Apollo come after?
By the time Surveyor was being planned, yes. Ranger wasn't, though. So Ranger had been formulated pre-Apollo. And there was some inkling of doing a landing program pretty soon, but it wasn't fully crystallized until Apollo. So definitely the goals of Apollo very much influenced, if not the design, at least the priority of that program. That program cost about $495 million in 1967 money. That's the equivalent of about $4 billion today. It was quite an effort. So, yeah, I mean.
So for those not in the know, Caleb does lunar simulant research in the lab. So I have a question of, does any of your research utilize surveyor observations, or at least can you wind back the references to surveyor?
Yeah, certainly. So obviously today it's quite a ways back, and a lot of the science that was gained was very fundamental level science. But that fundamental level science, I mean, serves as the bedrock of everything. So as I mentioned, that alpha scattering experiment, showing that the lunar regolith, at least in the Mare regions, was mostly basalt, okay? Well, I study the FUV reflectance of both lunar soils and lunar simulants in the lab. Okay, well, a simulant has to be like the moon. It has to be, for a Mare region, a basalt, okay? So the best lunar simulants that we have are ones that take, if not an actual basalt, which there is a place in Flagstaff, Arizona. It's the San Francisco Formation. There's these volcanic lava cones. They're a really awesome thing. But anyway, that's a good basaltic soil analog. But if not an actual earth-based basalt like that, at least taking the various mineralogical components of that and kind of mixing them together and everything. So yeah, it definitely, and of course again the consistency, the geotechnical properties, that influences what we think about the grain size and the porosity and everything. So yeah, a lot of it reaches back to that, but there's been so much work done that it's a very distant relationship. Think of it being like a great-great-grandfather, you know.
Then we'll close with, is Surveyor your favorite satellite?
Ooh, favorite satellite.
Woo! It counts.
Well, one, technically it's a lander or a probe, so I don't know.
Oh, I didn't even think about that.
Yeah, but.
Thing to launch from Earth.
Favorite. Ooh, that's a tough one.
Is it A119?
Is it? No, we never launched that one. I don't know. Would have been pretty epic.
What if it was on the far side?
But epic, yeah. But anyway, let's see. You know, I'm going to just have to say Voyager.
Yeah.
I know it's kind of an obvious one, but it's because, I mean, my goodness, it's still operating today. You've been to Jupiter, you've been to Saturn. In case of Voyager 2, Uranus and Neptune as well. So, yeah, you know, I mean.
All right, everyone, let's give a big round of applause for Caleb.
Yeah, thank you.
All right, that concludes the main portion of the event. And now you can stick around for French-themed trivia. Angèle is French. She was supposed to be one of the speakers. And Sam asked if Tom was French. So he's not. But yeah, it's like not even like close. I know, that's what I was like. It's not. Samuel.hart@sweary.org if you have any complaints. Yeah, if you want to stick around, give us a couple minutes and then we're going to come by with some trivia sheets and some pens so you can play some trivia. blocky image? Is it A, Pac-Man, B, a Rubik's Cube, C, a Rickroll QR code, D, Space Invader, or E, Phooey? I don't even know what Phooey is. I don't think that's it.
No, that's on the side of a building. Also,
Yeah,
if you
that's
guys
not
could do us a
space.
favor and just write the letter next to the question number so that it's faster for us to grade, we'd appreciate it.
Please. I don't even know what Phooey is. You know what Phooey is?
Nope.
Does anybody know what Phooey is? Is Phooey even real? Is Phooey in the room with us?
I would not put it past Sam to put a fake answer.
Yeah.
He almost certainly did.
Yeah, I know.
He's put much bigger troll answers on these before.
All right, everybody guess. And we can come back later on if we need it. Seems like everybody's still conferring. All right, question 2.
Royal Astronomy. Which French king founded both the Paris Observatory and the Royal Academy of Sciences? A statue of this king is located in the town square of Lyon, France. Was it A, King Louis XIV, B, King Charles IX, C, King Philip IV, or D, King Napoleon I? Thank you for the sheer number of Final Fantasy games I've played for being able to read Roman numerals.
Sometimes I think Sam just likes to torture us. I don't know if it applies internationally, but I know in the U.S., like the number of feet that are up signifies something about the person and how they died.
I'm tempted to ask my. Oh,
For number 1, I think it was.
the pack under the invader.
For this one,
Royal Observatory. That's pretty old. I want to say that might have been Louis. Yeah. It definitely wasn't Napoleon because Napoleon was never technically king. He was emperor.
you're all in for a French history lesson, whether you wanted it or not.
Should ask Mona this one. See her next.
All right, everybody got an answer? Question 3. Name that observatory. The image to the right is taken deep in the heart of France. How do you clap in French? Featuring, no one got, thank you. Featuring which observatory? A, Sorbonne Observatory, B, the Paris Observatory, C, the Bordeaux Observatory, or D, the Marseille Observatory. I wish our observatories looked like that. It's a very nice looking observatory. And covered in copper, I guess?
Some of it. To be fair, there are ones like that in the U.S.
Yeah.
Not quite that fancy.
Yeah.
Oh, I'm sure.
All right. Everybody got an answer? Question 4.
French chronology. Many famous physicists are of French origin. Among the French physicists below, write the letter corresponding to the oldest. What? I think that's meant to say oldest to youngest.
No, I think it's oldest and youngest. Who are the oldest and who's the oldest and who's the youngest?
Ah, okay. That would make sense. All right. Was it A? Oh God, I can't speak French. Louis de Broglie. I'm
I
so
say De
sorry.
Broglie. I'm not gonna.
I'm gonna be honest. I have never taken French
I'm
class
not
in my life.
French.
I have no idea how to pronounce these. Blaise Pascal Gaspard de Coriolis.
Yeah, I know.
D. Charles de Coulomb. Or E. André Marie Ampere. Half right answers are given a half point. So if you get one of the two of them right, you will get half a point.
All right, and okay, first rule. The first letter has to be the oldest. The second letter has to be the youngest. If you flip it, I don't care. It's wrong.
Yes.
Two answers.
You'll be listing two letters.
Answer, comma, answer. Now, to Adam's question, when? I have no idea. I'm guessing they're separated enough that it's like not a question, but a lot of physics happened between the 17 and 1800s, so I guess
going
like
to assume it's probably like when they were born.
yeah, I get like when.
Knowing the logic that Sam tends to go with these, that would be my guess.
Yeah, when did they start? More or less, yeah.
We also don't have a key right now.
Yeah, I noticed.
I mean, we have it obviously in the slides.
Yeah, I don't know. Yeah, we have to grade afterwards, which is fine.
We'll figure it out.
This is why Sam needs to be here. But it's okay. I know stuff happens. I don't know why he's not here. All right. Everybody have an assortment of answers? Like I said, we can go back if necessary. Question 5. Name that statue. The statue below shows which famous physicist born in Lyon, France. Is it A, Louis de Broglie, B, Blaise Pascal, Blase, C, Gaspard de Coriolis, D, Charles de Coulomb, E, André Marie Ampere. Hint, this answer differs from the last question's answer. Okay. I think I know who that is.
It looks familiar. Could not tell you which one of them it is.
And Sam just cropped out the name. Good for him. For me, the only reason this face looks familiar. Hey, whoa! Wait, back it up! Oh, okay, he's not playing. It's cool. The only reason this face is familiar for me is because Veritasium does animations of physicists, and this face looks vaguely familiar, but they all kind of look like that, so. All right. Question 6.
Higher heights. Now an emergency shelter, Refuge Velo, at 4,362 meters altitude near the summit of blank in the French Alps was once used to conduct high altitude research. Was it A, Dents Blanches, B, Der Matterhorn, C, Grand Coben, or D, Mont Blanc?
All right, does anybody need a question repeated? All right, if you say so. All right, everybody's good? All right, this next question will go in the bonus section. It is a bonus question, so it goes in the bonus section. At the E. coli, no, E. coli, Nationalis de, oh my God, de Ponce et.
French people, can we talk about the length of your names? It's almost as bad as the Germans.
It's just like, National School of Bridges and Roads. One will find this bust depicting which French physicist at his alma mater. Last name only is sufficient. Hint 1, he is famous for 2 equations. One describes solids, the other describes liquids, quote unquote. Hint 2, he worked closely with 2 other famous physicists for his 2 famous equations. Because I saw the slides, but the hints are very, they kind of help, but they kind of don't. They do, but they don't.
You're asking the wrong person right now.
I didn't realize.
Liquids, it means gases.
Yes. Yes. It's the one and only. But that's the first one. That one I know because I looked at the slides. Hell yeah. Yeah. Not even. Not in my purview. That would be a crazy undergrad course.
It was, I had a couple of friends who were doing it when he was like in 2 years before me. He's now in math and
It's just, it's math. The physics is like.
And that is never pretty well with my point. Stats? Stats I can do. Stats make sense to me.
That does not make sense. Never will.
The other thing is stats is kind of funny.
Yes.
Formulas are the same, but really right.
Yeah.
That's a bit. That's a problem. Like I still have stats that are now analysis for my test. So it's like, okay, how many data points do I actually need before when I'm
Yeah,
saying
of course.
yeah.
All right. Last chance. Anybody need a question repeated? Okay. When you are done, please bring up your answer sheet to us. That is the easiest thing for us. And if we gave you a writing utensil, We are not funded. We need your pens. We need our pens back, please.
Everyone who grabbed a
Thank
sheet
you.
should be bringing up a pen because only 2 groups already
Thank
had
you.
a pen.
Thank you. 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 Wow, everyone is so nice. They brought their pens. Thank you, Mark. I hope one day there's a Rick roll in space. I live for that day. Question 2. Question 2.
Really, Sam? All right.
Oh my God, Sam.
Which French king founded both the Paris Observatory and the Royal Academy of Sciences? A statue of this king is located in the town square of Lyon, France. It was A, King Louis XIV.
That's him. He's fired.
To be fair, he was fired several times over tonight for
Yeah.
various infractions.
Of course, he's wearing a Sweary shirt. Like, come on. And then the observatory, Sorbonne. I don't know French geography. I don't know where these places are.
All
And
right.
then, so for the two scientists, oldest to youngest, several of you did it backwards, which I find interesting.
So the French chronology. Louis was the youngest, and Pascal was the oldest.
Wow, he was almost 100. So I knew Louis de Broglie was the youngest because we had to study quantum mechanics, and like it's a whole thing with like the wavelength. He did like the wavelength of like solid objects. Like I don't know how to explain it, but yeah, several of you did it backwards, which is kind of interesting. I think I can understand why, because Pascal is like pressure, if you know it's pressure, and so, well, yeah. Yeah, so they were all, well, no, not all, okay. How did Sam do this? Well, I guess the oldest and the youngest are definitely the oldest and the youngest. But the other three, they're all contemporary. So I don't know how Sam would have done that. But anyways, question 5 was,
Of course he.
when did he go to France?
I think he photoshopped himself in.
No, did he? Is that photo?
It kind of looks like it. Maybe not the other one. That
When
one
was he in
photoshopped.
France?
Yeah, he went to France not all that long.
So he's been waiting to do this. He's just been wanting an excuse to do French-themed trivia.
Also, as a fun little tidbit about this one, you could actually find the name on the statue. You could, in fact, read it on the screen previously, just not from y'all's part of the room. It is right here at the bottom
That's
of the
why
statue.
Sam is fired. Yeah, most of y'all can't see it. We can.
Yeah.
So he got away with it, only
Yeah.
because of biology. And then question 6. Name that mountain.
Higher heights. It was Mont Blanc.
Mont Blanc. White Mountain. Any guesses why they call it White Mountain? Snow. And then, oh, the bonus, name that physicist. Claude Louis Navier. So the first hint, I don't know what the first equation is, but the second equation is liquids. It's fluids. It's the Navier-Stokes equation. Yeah. What are the guy? Stokes? Oh, yeah, I guess it was Stokes, whoever Stokes is. Yeah. I don't know. Ask Sam. He's the French know-it-all, apparently. And now for some prizes. Third, right, yeah. So, in third place, winning last year's edition of the Night Sky Almanac. The night sky maps are old, but the information is still valid. And a Europa Clipper, a little foldable, and some stickers. Water, name, fire. Y'all just like pick one? It worked out because there's 3 almanacs and there's 3 of you, so. In second place, winning some Celestron hats and some more stickers. CNC machine. They won by a half. Complained to Sam. Or they got second by a half. And then in first, they got the bonus correct. They kind of got the bonus. They got the bonus correct, but they were like Stokes? Question mark. No mercy or no mercy. Little powerhouse over there. Oh, so you're winning 4 actual lunar photos from Lunar Orbiter, I think is what it's called, courtesy of Robert Reeves. Robert Reeves, he's not in the building anymore, but yeah. We thank Robert Reeves for giving us these every month. And I'm glad someone new got to have some photos, because a lot of the times, just saying people win. Yeah, they go to Caleb. All right. That's our show, folks. Thank you for coming. Next AOT is July 2nd. We'll see you then. It's before the holiday, so you haven't left yet, because it's still a work day. Special thanks to Blue Star, Sweary, UTSA. Follow us on our socials. Pick one, I guess. And if you want to sign up for our email list, here's a QR code. I think most of you are on it, actually. But yeah, thanks, everybody.